Hi everyone, I'm Joey Carlson. I'm with the Department of Electrical and Computer Engineering at University of California, San Diego. I am a PhD student with Professor Robert Heath, and today I'll be presenting our work titled Tri-Hybrid Signal Processing for Interference Mitigation in Mobile Ad Hoc Networks. So first, I'll get into the motivation and background for this work. So multiple antennas are critical and crucial for mitigating interference in mobile ad hoc networks. If we want to shape beam patterns to create different nulls and steer towards target users, as we can see in the figure on the left, using multiple antennas is really crucial for that. And so if we want to be able to null out that interference, we want the multiple antennas, but at the same time, if we create really large antenna arrays with lots of capabilities for shaping the beam pattern, that is also going to come with a lot of power consumption and hardware cost. Our RF front end may have DACs or mixers and all these other things that start to really add up as we increase the number of antenna elements in our array. And so we both simultaneously want the high performance of having large arrays to shape our beam pattern how we want to communicate with target users and mitigate interference from unwanted users. But at the same time, we don't want to significantly increase our power consumption and hardware costs. And so we want to come up with a solution to this. How can we have the high performance with the low hardware cost? So there's a couple of different beamforming strategies that we could use in a mobile ad hoc network. First, we could implement a fully digital array. And so each antenna on our array has its own dedicated RF chain, and we can do digital signal processing to shape our beam pattern in many different ways, or to do whatever arbitrary signal processing we want to. Of course, this is great. This has we can achieve optimal communications in this way, but this will come at the cost of very high power consumption. So many components, high cost, high power. Next, we could use a phased array. So instead of having a dedicated RF chain for each antenna could be connected to its own phase shifter. And this still has many components and some power consumption, but less than the digital array, and still great beamforming capabilities. And so we sacrifice a little bit of beamforming capabilities for some hardware costs. Now, but we want to go one step further. We want to create really, really large arrays with very, very low power consumption and cost. And so what we've been looking into is a reconfigurable antenna array, as we can see on the figure on the right. So rather than having phase shifters or many RF chains, we just need a simple power divider, and the antennas themselves are actually reconfigurable at the antenna level. And so tunable components can be integrated into these, and you have an external control that tunes the electromagnetic properties of each of the different antenna elements. And so no extra RF chains, no extra phase shifters. We can tune our array and shape our beam pattern without any of that, just with an external controller and small tunable RF components. Naturally, we will sacrifice a bit of beamforming with this, but with the power consumption savings and the hardware costs, we think that this is well worth it. And we've been looking into different ways to improve the performance of our reconfigurable antenna arrays. And so one promising technology or one promising design for a reconfigurable antenna array is the dynamic metasurface antenna. And so dynamic metasurface antennas are these reconfigurable slotted waveguide antenna arrays. And so we have a waveguide, and when we excite the waveguide, small slots are etched atop the waveguide that then resonate and radiate out power. So this is a sort of a type of linear slotted waveguide antenna array. The key thing here is this geometry is very specific, and you can integrate varactor diodes or other tunable components into each of the different etched elements to enable beamforming. These varactor diodes have low power consumption. They're these tunable capacitors, and so by tuning the capacitance of each of these varactors, you can actually change the effective antenna weights on each of your antennas and enable beamforming. And so this is really the key to enabling the low power, low hardware cost MANET for interference mitigation, is using these dynamic metasurface antennas with varactor diodes. Now, of course, lowering the power consumption will come at some costs, and of course, and here it's going to be in some of the beamforming limitations. So now we're going to have a restricted weight distribution, so there's going to be a much smaller range of antenna weights that we could use for beamforming or signal processing. And because of the waveguide architecture of DMAs, there's also going to be some complicated scattering that we need to account for. So if we want to still have that best performance that we're looking for in our MANET, how can we overcome this with just the DMA? Well, our answer to that and what we've been looking at recently is what we're calling the tri-hybrid architecture. So rather than having the hybrid architecture, which is digital and analog signal processing, we're going towards tri-hybrid, which is digital, analog, and reconfigurable antenna signal processing. And so we have 3 different layers of signal processing, and this will help us to overcome some of the limitations for the DMA. So if there's limited weights for the DMA, we'll have these additional analog and digital signal processing to help overcome those limitations and fill in the gaps where maybe the DMA performance would be a little bit lower. And so having the analog and digital signal processing is really important to help overcome some of the DMA limitations. Now, prior work on DMA beamforming has largely focused on single beam steering, so forming a beam pattern to steer towards a target user, and even some hybrid DMA communications where we have a joint DMA and digital signal processing. But there's a huge lack of work that's looking at both interference mitigation for DMAs and extending to the tri-hybrid architecture. And so we wanted to investigate this because we think that the use case is really important, where MANETs, there could be battery limited devices where we really want low power and low hardware costs. We can manufacture them quickly and cheaply and not have large power consumption. So we think this is a great scenario and case to use the tri-hybrid architecture, and we wanted to investigate the performance of using the tri-hybrid architecture in this MANET specifically for interference mitigation. Now we'll go into some of the technical details for doing interference mitigation with the tri-hybrid architecture. So here we see the problem setup for the tri-hybrid system. On the left, we have our DMA planar array, where we have a tri-hybrid receiver here, and we have our target TX user that we're trying to communicate with, as well as multiple interfering users whose signal we want to mitigate. Now, at each of the different points of the tri-hybrid architecture, we have a unique combiner. So we have the DMA combiner that goes with the DMA weights, a phase shifter network where each phase shifter is connected to a linear DMA subarray, and then lastly, our baseband digital signal processing. And so the combination of all 3 of these combiners forms the full tri-hybrid combiner. And we can see the structure of each of these different matrices in the figure below as well, where we have this block diagonal structure due to the partially connected structure of the DMA with the phase shifters and then the phase shifters with the RF chains as well. And so given this complexity and given the different, the DMA, phase shifter, and baseband combiners, how can we configure the tri-hybrid architecture to effectively mitigate our unwanted interference from unwanted users? So the tri-hybrid signal model and SI&R model that we'll be using is what we show here. We use a clustered channel model where each of the different users emits their signal, and a single cluster with multiple arrays impinges upon the tri-hybrid receiver there. And then with this channel model, our received signal model is simply the combination of the signal from the target user with a specific power and large-scale path loss in the channel, as well as the received signal from each of the different interfering users and the noise as well. And so this is a classic received signal model for a scenario with a target user and multiple interfering users, and we can then formulate our SI&R objective as seen in the bottom left-hand corner, where we want to maximize the signal from our target user and minimize the signal from our interfering users. Now we want to discuss the DMA beamforming weights and how we can model the DMA in our tri-hybrid combiner. And so the effective DMA beamforming weights can really be summarized into 2 different parts. On the left, we show there the reconfigurability term, And that is really due to the varactor diode. So when we tune that varactor diode, that allows us to change our effective antenna weights. And it turns out that that reconfiguration follows what's called a Lorentzian constraint. So we see that in the blue curve there. And we immediately see that compared to a unit amplitude distribution, this is much more restrictive. So our antenna weights do not have a full 360-degree phase range, only 0 to -180. And there's also a coupled amplitude constraint. So it's really quite a complex weight distribution to work with for doing this complicated signal processing for maximizing the target user, minimizing the interfering users. Moreover, there's also a scattering term in our effective DMA weights that has to do with the forward scattering from the waveguide when each of the different DMA elements resonates. And this also significantly complicates the distribution because we have this product term, so now all of the different elements are sort of independent on one another due to the forward scattering of each of their different resonances. And in addition with the waveguide electromagnetic fields that impinge upon each of the DMA elements and cause them to resonate, of course, the fields have an inherent phase advance. And so this needs to be accounted for as well. And we account for this in the DMA array response vector as seen on the right there. And so it's very similar to it's very similar to the classical DMA or array response vector, but with this extra waveguide phase propagation term there, shown beta G. And so all these different things accurately allow us to accurately model our DMA elements in DMA array. However, it's quite complicated with there's the scattering, the waveguide phase propagation, and the limited DMA weights from the Lorentzian constraint. It's not quite clear how these weights should be configured to maximize the SI&R in our scenario. So to maximize the SI&R of our trihybrid combiner, we leverage a genetic algorithm. And so this genetic algorithm allows for a smart search over the large combining space of the DMA and phase shifter weights to come up with a solution with a high SI&R. And so the algorithm works by first randomly initializing the trihybrid configurations, so coming up with random combining weights for the DMA and phase shifter matrices. Evaluating our cost function, which in this case we want to maximize the SI&R, selecting some of the best performing trihybrid configurations based on this cost, and then implementing some random mutations within the combining matrices for the DMA and phase shifter weights as well. And then over many iterations, the solution converges, the configuration for the trihybrid architecture converges towards a solution with a very, very high SI&R. And so although the process is completely random, it allows for a search over many of the different weights that ultimately ends up with a very high SI&R solution to mitigate the interference while still enabling good communication with our target user. And so in addition to the genetic algorithm, we also wanted to implement an algorithm that was more analytical rather than having a large search space. And so we came up with this simple greedy algorithm. And so the main idea is that we want to leverage the DMA and the phase shifter or RF combiners to align with the target user channel. So we want to really dedicate those two parts of the trihybrid architecture to communicating with our target user. Then we want to use the digital combiner given the combiners for the DMA and RF that have already been set. We want to use the digital combiner to then mitigate unwanted interference from the rest of the users. And so that is really the main idea of the greedy algorithm. It's a low complexity, fast algorithm to test against the genetic algorithm and see how important it is to use the genetic algorithm to have that large search space to configure the trihybrid architecture. Now we want to show some simulation results for our trihybrid communication system. And so first we will be evaluating what I'm calling a friendly scenario. So in this scenario, our target user is close to our trihybrid receiver, and we have friendly users in the background who are not communicating with or emitting signals with a super large transmit power, and they're further in the background as well. And so this is sort of a low interference scenario. So how can the trihybrid architecture do under low interference while communicating with a target user. We have some of the DMA parameters for the tri-hybrid architecture and the fully digital benchmark listed above. And it's important to note that because DMA elements are sub-wavelength, they're quite small, they can be spaced a little bit more densely than you would maybe a typical antenna array. And so we're actually utilizing here 72 element array for our tri-hybrid architecture with a lambda over 4 spacing in the X direction, whereas for the fully digital benchmark, we stick to the classic lambda over 2 spacing with 36 elements. So the aperture size remains the same for both cases, but the DMA case is more elements due to that sub-wavelength design. So now in looking at the spectral efficiency results as a function of both the desired user power and the number of interference users, we can note a couple of interesting things. First, the DMA-only tri-hybrid case and fully digital optimal combining solutions all provide pretty much the same performance. It's very, very close. The DMA-only case and tri-hybrid do great compared to the fully digital combining solution across both cases, even when there's more numbers of interferers. And so this really shows that for a scenario with lower interference, where really we're just trying to communicate with a target user, the DMA-only case does really, really well with the genetic algorithm. And so the genetic algorithm can really come up with a good solution to communicate with the target user. And then also the greedy algorithm starts to fall really far behind and does not perform as well as the DMA-only case. And that really shows how the complexity of the DMA weights and how it's quite difficult to come up with an analytical solution for maximizing the SI and R. The genetic algorithm is quite important. But one criticism of the previous slide could be, well, the DMA-only case and the tri-hybrid case are very, very close in performance. Why do we need tri-hybrid? And so we also wanted to evaluate a high interference or jammer scenario, what I'm calling it. So here the target user is further away from the receiver than the interfering users, and the interfering users have a high interference power. So they're transmitting a high power signal higher than the target user, and they're much closer to, so the path loss is less. And so here really there's a lot of interference, and so we need good signal processing to mitigate that interference and communicate with our target user. So now when we look at the results, we see quite the opposite as the previous slide. The DMA-only case now starts to fall significantly behind and has much lower performance than the tri-hybrid architecture, while the tri-hybrid architecture still performs almost as good as the fully digital optimal combining solution. So here we really see the benefit of tri-hybrid when we have high interference and we need more complex signal processing with more flexibility to mitigate the interference. The DMA-only case can't quite handle that, whereas the extra phase shifters and RF chains in the tri-hybrid architecture are crucial to help us recover our target user signal and mitigate the interference. And as the number of users increases, we also see that the tri-hybrid architecture starts to decrease, and that is also due to the lower number of RF chains in the tri-hybrid architecture. So this really shows that even with just a few RF chains, here we have 3, if our number of users remains within that, if our number of total users remains within that, then we can still enable really, really high performance close to the fully digital optimal combining case. And now lastly, we also wanted to see how resilient the DMA-only and tri-hybrid cases are to multipath, and so we also varied the ray spread from each of the clusters in our simulation results to see that. And as it turns out, the DMA-only and tri-hybrid cases are quite resilient to multipath, and really the spectral efficiency and performance does not change significantly. The curves remain pretty much the same for both cases. And this is really interesting to see, and to see that both of these cases for the DMA and tri-hybrid are quite resilient to the amount of angular spread and the spread of these different paths. So really, this is a great result to show that the tri-hybrid and DMA cases are very resilient to dynamic and rich wireless environments. So now we'll go over some of the key takeaways of this work and our future work. So in this presentation, we went through the tri-hybrid architecture and leveraging the tri-hybrid architecture for MANETs. We had a tri-hybrid architecture with our dynamic metasurface antenna, our phase shifters, and RF chains, and we configured it with a genetic algorithm to come up with high SINR solutions that operated really, really well under high interference scenarios. And so when we compared under our jammer scenario, the DMA only case to the tri-hybrid case, the tri-hybrid case was able to provide excellent SINR and spectral efficiency results that approached our fully digital combining solution, whereas the DMA only case couldn't quite achieve that performance because of the extra flexibility in the tri-hybrid architecture with the phase shifters and RF chains. Now, the current work focused on having target and interfering users with just a single antenna, so no pre-coding really, and then using that genetic algorithm to have our smart search over the many different possible DMA and RF weights. In our proposed work, we want to take this a step further and really leverage maybe user feedback and have multi-antenna pre-coding to do a joint pre-coding combining optimization problem to mitigate interference and continue to boost our SINR and resiliency in our system, as well as potentially improving upon the greedy algorithm or the genetic algorithm to go towards real-time communications in our system. So thank you so much for listening, and for more information, please refer to the full paper. Thank you.